Hello, everybody. Welcome to our CEE159 final project presentation. Today, we're going to talk about the green redesign of Miles Avenue Elementary School in Huntington Park, California. This is our team.
As an introduction, we've aligned our design goals with the Los Angeles Green New Deal plan. Some of these include increasing renewable energy and water sustainability, which will be outlined in a later slide. The site we've selected is Miles Avenue Elementary, and our overall goal is to outfit this campus with green infrastructure. And here's a geographical reference for Miles Avenue. Its specific location is Huntington Park, Los Angeles, as previously mentioned. The physical site is approximately covered by 86% impervious surfaces. Additionally, the school is located in an area that has been identified as a disadvantaged community by Cal EPA, and these are some of the reasons we selected the site for green infrastructure outfitting.
So this was a site that we chose to outfit with green infrastructure. The total area sits at about 38,000 meters squared. As you can see, there's large unutilized spaces, there's a large blacktop area. About 15% of this area is covered with trees and 86% is covered with impervious surfaces, of which 31% is buildings, so that can't be changed. But the other 55% or so, we wanted to try to incorporate some green infrastructures. We were designing for the 85th percentile 24-hour storm intensity, and that's the number we used for our green infrastructure calculations.
In this project, we set out to accomplish three related goals. The first was create self-sufficient energy and water cycles, meaning we wanted to build green infrastructure that would capture enough energy and water to sustain the energy and water demands. The second goal was to promote sustainability, education, and health, which are achieved by the very presence of natural greenery and exposure to the green infrastructure. The third was a goal that would be related and resultant from the first two goals, which is reducing pollution and the urban heat island effect.
So this is the map of the site after our green infrastructure implementation. We cut the amount of impervious asphalt in half. We incorporated over 40 community garden plots and incorporated over 1,000 meters squared of bioswales and other native vegetation. We also rearranged the playground areas and incorporated over 4,250 meter cube of turf playing fields. And we also added solar panels to the roof to cut down on energy, but the rest of the team will expand on that later.
So now we're going to go through the energy cycle analysis. So Miles Avenue Elementary School has a total population of 980 students, which is a relatively high population. For this reason, we use the 95th percentile energy demand and to calculate the demand value of 13,728 kilowatt hours per year. We believe that solar panels is the solution to this dilemma. You can see here that we're going to install the solar panels on one of the roofs of one of the main buildings. So we believe that the system size that would be the best combination of energy capture and price would be 94.4 kilowatts. The system size would have an upfront cost of $283,000, which seems like a lot. However, the annual production from the system would be 155,000 kilowatt hours. And when you calculate the net annual revenue that the system would generate, it would be around $23,000. The payback period for this system would take around 12.5 years, which is about half of the system's lifespan. So that means the system would generate about $280,000 in revenue following the payback. Now we're going to go through the water cycle analysis. So Miles Avenue Elementary School has a water consumption of about 6,700 cubic meters per year. So we decided to implement green infrastructure to try to satisfy this demand.
Proposed green infrastructure is natural turf, and Bermuda grass is our selected grass species for this turf, as it is a native species to Los Angeles and is able to resist its dry climate, so it requires less irrigation than other grasses. It can serve as a field for athletic use and has it has the ability to reduce the urban heat island effect?
So we propose the implementation of an extensive green roof on our site. It would sit on top of the existing parking structure, which is already used for recreation. For this reason, we believe it would be a good site for an athletic field. And we chose Bermuda grass as the vegetation that would be the best fit for the site. And we also chose 20 centimeters of soil for the growing medium, which would reduce irrigation demand. And then the rest of the layers of the green roof would be the standard layers. And this green roof would capture about 476 cubic meters of water per year.
So one of the biggest issues at Miles Avenue Elementary School is that it's covered by 86% impervious surface, most of which is blacktop in the parking lots and on the playground. This surface contributes to both increase in runoff and pollution of stormwater, as well as raising the temperature of the school grounds due to the urban heat island effect. To mitigate these issues, we decided to install permeable pavement in the school parking lot, on the playground, and on the running track, as it allows for water to infiltrate into the ground during rainfall events, which reduces surface runoff and has the potential to reduce the urban heat island effect through evaporative cooling. So since our project design requires a lot of water to maintain, we decided to include an underdrain with a raised outlet and an impermeable liner below the reservoir layer to maximize stormwater capture. So we use 3 different types of permeable surfaces. So for the main playground, we use pervious concrete. For the parking lot, we chose permeable interlocking concrete pavers. And for the running track, we used 100% recycled rubber. So the total volume of water captured by the permeable pavement system is estimated to be 1,391 meters cubed per year.
So with design goal 1 and 3 being stormwater capture and decreased urban heat island effect, we decided that it would be beneficial to install a biofiltration swale next to existing drainage and along the edge of the parking lot. So as you can see in this diagram, we have 2 impervious catchment areas that will remain impervious after all other green infrastructure installments. And we calculated the sizing for bioswale 1 and bioswale 2 based off of these catchment areas and the characteristics of the site. And then in this diagram on the left, I kind of illustrated what these swales will look like from the side. Obviously, they will both have different widths, but they'll follow the same formula for each of the components. So the swales will have rocks placed at the inlet for the pre-treatment phase to avoid flooding the bioswale and risking erosion or reduced infiltration. And then for the plants, we're going to plant native species that don't require as much water, but they can still ensure stormwater capture without needing to have a lot of maintenance. Then the retention area was calculated to be 1.5 feet deep for the ponding, just to maximize infiltration and groundwater discharge. And then for the filter media layer, we'll have a 3-inch layer of mulch on top of a mixture of sand, topsoil, and compost for the bioretention mix. And the recommended depth for that is about 3 feet. And then this transition layer will just be coarse sand. And that will just help further the infiltration and capture extra pollutants. And for the drainage layer, we will have a perforated pipe running through a layer of gravel. And then that treated water will be collected from the underdrain and sent to a catch basin for reuse. And so based off of our calculations, we estimated that the bioswale would capture 51.6 cubic meters of water per year. And not only will the bioswales help with stormwater capture and decreased urban heat island, it's also just generally an enhancement of the aesthetic values of the community. And it will just basically benefit this campus.
To collect the stormwater that will result from an increase of permeable surfaces, we would implement an underground cistern that will collect water from the green infrastructures. Before it reaches the cistern, it'll go through a hydrodynamic separator for filtering and then into the cistern. We'll then reroute this filtered water to the community garden to improve the school's water sustainability.
And here is our annual water cycle. Although we project that the water cycle will not be self-sufficient and design goal 1 will not be met, we believe that a lot of the costs that we incur in terms of water costs will be used to help us create a self-sufficient energy cycle, as well as meet our various other goals that we proposed previously. And now we'll talk about the social benefits. So for the social benefits, we propose to build a community garden using planter boxes to grow nutritional food crops as well as native species. Teachers and students can plan what food crops to grow. And as for native species, according to the LA County Drought Tolerant Garden Handbook, we could plant the Malva rose as well as the scarlet monkey flower. This will confer benefits such as addressing food insecurity, as 96.1% of the school population is from socioeconomically disadvantaged backgrounds, and the food can be integrated into school meals, into take-home meals for the family, as well as for donations to food banks and the local community. It would also encourage more social integration between local and immigrant students, as 39.1% of the school is ESL speakers. So there's a lot of research showing that collectively engaging in a community garden will help improve social cohesion. And at the same time, the teachers can design sustainability educational curricula surrounding the community garden to learn about nutrition and agriculture. And all in all, research shows that this improves the students' physical and mental health as well as academic performance.
It has been noted that the implementation of green infrastructure can have positive health and developmental effects on children in school. The addition of green infrastructure helps to increase the social capital of an area by increasing the space for the community to come together and interact with one another. In schools, it can also block out excess sounds and pollutants, which will help mitigate stress that students experience throughout the day, resulting in the students having a better environment to learn and engage with their schooling.
And finally, we'll be touching on the urban heat island effect. So to address this, we propose increasing tree canopy coverage at Miles Avenue. Trees can decrease surface and air temperatures through shade and evapotranspiration. Increased green space also has numerous health benefits, as Seth just mentioned, and they can also help decrease runoff volume by intercepting rainfall and increasing the lag time during a rainfall event.
To conclude, we have 4 main points that our project fixed. We wanted to reduce the water runoff at Miles Avenue Elementary, and especially do this while decreasing the peak rainfall intensity and untreated runoff that will be entering the sewage system and will remaining untreated on the surface in stagnant puddles. We also wanted to ensure that we'd be able to satisfy the energy demand of the school through solar installation, and we wanted to improve the social capital and learning environment for children in the area.
Thank you very much. Any questions?